Chapter 1. They're not supposed to crash. In the age of AI, titanium alloys and fly-by-wire systems, commercial jets are the most over-engineered, tested and monitored machines humans have ever created. They operate in a zone where pressure is 1/5 of sea level, temperatures drop below -50 degrees Celsius, and there's no room for second chances. So when an aeroplane crashes, something so statistically rare that you're more likely to be struck by lightning twice in the same day, it isn't just a tragedy. It's a systemic failure, a scientific case study, a perfect storm of engineering, physics, human decision-making, and raw chance. Let's reverse engineer how these failures unfold, from airborne stability to catastrophic collapse. Chapter 2. Lift, Thrust, Stability. Why flight works at all. To understand a crash, you first have to understand why planes don't fall. An airplane in level flight exists in perfect equilibrium. Lift counters gravity, thrust counters drag, and control surfaces ensure balance in pitch, roll, and yaw. Wings are shaped as airfoils, slightly curved on top, flatter below. This geometry accelerates airflow over the top surface, lowering pressure, while Bernoulli's principle, while the bottom faces higher pressure. Net result, lift. But here's the critical part. Lift isn't automatic. It relies on airspeed, angle of attack, wing configuration, and air density. If even one of those variables goes out of range, the wing loses lift. The plane stalls, and the countdown to disaster begins. Chapter 3. The cockpit computer, the human-machine interface. In modern jets, the pilot doesn't directly control the wings or engines. Instead, they communicate with a digital flight control system, fly-by-wire computers, that translate joystick and throttle inputs into precise commands for ailerons, roll, elevators, pitch, rudder, yaw, flaps, slats, lift optimization, spoilers, drag and descent, thrust reversers, braking after landing. These systems include redundancy by design, triple electrical buses, backup hydraulics, isolated power systems. Yet every layer of automation is still vulnerable to one thing: corrupted inputs. When a sensor malfunctions or data becomes ambiguous, the flight computer can act in good faith, but make the wrong decision. Which brings us to Chapter 4. Software that fights the pilot. Boeing 737 MAX. In the case of Lion Air 610 and Ethiopian Airlines 302, both crashes involved a hidden system, MCAS, Maneuvering Characteristics Augmentation System. MCAS relied on a single angle of attack sensor to determine if the nose was pitched too high. If it thought the nose was up, MCAS pushed it down automatically. But when the sensor failed, the system went rogue. It forced the nose downward repeatedly despite the pilot's attempts to counter it. The trim stabilizer moved to dangerous angles. Manual override failed. Alarms flooded the cockpit. Both jets nosedived into the ground, killing 346 people. This wasn't a hardware failure. It was a software-induced aerodynamic failure, with the pilot locked in a losing battle against the very system meant to protect him. Chapter 5. When the sky turns hostile. Weather-induced crashes. At high altitudes, even tiny changes in temperature or humidity can wreak havoc. Icing adds weight, alters wing shape, and blocks pitot tubes used for airspeed. Thunderstorms generate updrafts and microbursts, vertical wind blasts of up to 6,000 feet per minute, too fast for human response. Wind shear during landing can rob a wing of lift instantly. In 1985, Delta Flight 191 was on final approach into Dallas. A microburst from a thunderstorm hit the plane. The aircraft dropped 300 feet in 2 seconds. Engine spooled up, but too late. It slammed into a water tank short of the runway. 137 lives lost. There was no mechanical issue, no pilot error, just a burst of angry air, undetectable with the radars of that era. Today, predictive weather radar and LiDAR systems help spot these dangers, but not always in time. Chapter 6. The Stall. Invisible Killer. Let's say your engines are running, your instruments work, visibility's perfect, but your nose climbs just a few degrees too high, and your airspeed drops below the critical value. Suddenly, airflow detaches from the wing. The smooth stream breaks into chaotic vortices. Lift vanishes. That's a stall, and it doesn't mean the engine stopped. It means the wing stopped flying. Stalls are recoverable, but they require quick recognition and counteraction. Lower the nose, increase thrust, regain airspeed. In 2009, Air France Flight 447 encountered ice crystals over the Atlantic. Pitot tubes froze. Autopilot disengaged. The plane stalled, and for 3 full minutes, the pilot unknowingly kept pulling up. The Airbus A330 dropped from 38,000 feet to sea level. All 228 souls lost. The stall wasn't invisible. It was ignored. In the dark, over the ocean, confusion reigned. Chapter 7. System Cascade. The domino effect. Crashes don't always start big. Sometimes it's just a cracked seal, a miscalibrated valve. But in an airplane, systems are interlinked: hydraulics, avionics, pneumatics, electrical, flight controls. One failure can trigger 10 more. A ruptured fuel line leads to a fire. The fire disables hydraulic pumps. The loss of hydraulics disables flight surfaces. The airplane becomes uncontrollable. That's exactly what happened in Japan Airlines Flight 123. A faulty repair on the rear pressure bulkhead caused a rupture mid-flight. The explosive decompression tore off the vertical stabilizer, disabling all hydraulic lines. The pilot struggled for 32 minutes, trying to control the aircraft with engine thrust alone. Eventually, the Boeing 747 slammed into a ridge. 520 people died, the deadliest single aircraft crash in history. Chapter 8. Redundancy with limits. Every critical system on a plane has backups. Triple inertial reference units, dual autopilot channels, independent left-right power buses. Yet even redundancy fails when multiple systems go down simultaneously, especially in electrical or fire-related incidents. In 1998, Swiss Air Flight 111 caught fire in the cockpit due to faulty insulation near the entertainment system wiring. The crew tried to troubleshoot, but within minutes fire overwhelmed the avionics bay. The aircraft lost attitude control, pitch trim, and eventually crashed into the Atlantic at 300 knots. There were no survivors. The autopsy? Not engine failure, not pilot error, wiring design. Chapter 9. Before the crash. What happens in the final minutes? The moments before a crash are rarely chaotic in the way that movies portray them. Cockpit recordings often show the crew calm, focused, desperate to regain control. You hear, "Flaps 30, pull up, engage ultimate law, terrain, terrain." In the cabin, passengers might not even sense disaster until the descent becomes too steep or a sound changes. The final seconds are usually filled with attempts, restarts, control tests, speed corrections. Not panic. Impact comes silent. Chapter 10. The Aftermath. What we learn from every crash. Every crash is a data point, a lesson. Black boxes, the flight data recorder and cockpit voice recorder, store everything. Speed, altitude, pitch, or yaw and roll angles. Every word said, every switch flipped. Investigators rebuild the crash second by second, and as brutal as it sounds, aviation gets safer every time a plane crashes. That's why modern jets are 1,000 times safer than 50 years ago, because every failure leads to a fix. We fly today on the lessons of yesterday's tragedies. You're safer than you think. Airplane crashes are terrifying, but they're also the most studied, prepared for, and engineered scenarios in transportation. For every system that fails, 5 others are designed to compensate. The next time you buckle your seatbelt and hear the engines roar, remember, you're flying on science, redundancy, and hundreds of years of lessons paid in blood. And in that balance, there is safety.